Okay, so yesterday we ended up with our working in the near zone, second iteration of the relaxed Einstein equations, because we needed to get corrections of order gravitational potential squared or g squared in order to get a consistent metric to find the equations of motion. Yes, hello. We ended up with, we took the metric that was derived that way and plugged it into the covariant conservation law, the covariant derivative of the stress energy tensor vanishing. That's the fundamental equation of motion that you can use. You could also use that ordinary divergence equation with the Landau-Lifshitz pseudotensor. You're guaranteed to get the same answer, but this is, generally speaking, a simpler approach to use. And so we ended up with the Euler equation. Everything now written in terms of... Okay. Let's try Houston. Hi there. We now write all the densities, of course, in terms of this conserved density rho star. This is a post-Newtonian, well, it's actually an exact expression, but you can also expand it to post-Newtonian orders. But it satisfies an exact continuity equation. So it's a very useful thing when you're working at high post-Newtonian orders, because you can use all the old rules of the road to calculate things like time derivatives of potentials, as long as everything is written in terms of this rho star variable. So the first line is Newtonian limit, standard Eulerian and hydrodynamics, and then we have post-Newtonian corrections, and then we're going second post-Newtonian order and higher corrections for the moment. The next goal was to repeat what we did in Newtonian theory, try to find equations of motion for self-gravitating, well-separated bodies whose separation is large compared to their size, they're isolated. We will not worry about high multiple moment interactions as we did in Newtonian theory. Larger, because post-Newtonian theory is already complicated enough, but in principle you can do it. And we will assume our bodies are reflection symmetric. It's not a bad assumption for sort of realistic perfect fluid bodies. Mainly it says you're not you're ignoring pear-shaped bodies, so you're not worrying about weird asteroids. But for most perfect fluid bodies, it's good. It's a good one, and we'll see in a moment that allows us to throw away certain terms that really don't matter. We then define our mass, position, velocity, and acceleration of each body by simply integrating the appropriate variable over the center of mass. And I preached a little bit about why that's a useful definition of the center of mass, but you should not. It's a waste of time to worry about some more fancy or rigorous definition, because all you really need is a self-consistent definition that allows you at the end of the day to translate everything into observable quantities, such as the time of the radar signal to bounce off the surface of the planet and come back as a function of time, allowing you to infer by some algorithm what the motion of the center of mass is and whether that agrees with the equations of motion that you've derived. But these definitions are very nice and very useful because, again, they involve simply rho star, and so all the rules of the road that we talked about earlier could be used to just, manipulate like crazy and have fun. So, and let me give you an example of what might happen when you start to integrate these. So we want to take this equation of motion and integrate this over body A. Right? So we get ma times the acceleration of body A, and it's going to be equal to the integral of this over body A. Okay? And the potential, for example, has a piece coming from body A itself, but it also has pieces coming from all the other bodies in the system, so you have to break these things down. But I want to focus on one particular term because it will illustrate an effect that arises, and then we'll have to deal with. And let's just look at this term here: rho star v squared times the gradient of u. Okay? So that's the velocity of our body A, integrating this over body A, and that's the gradient of u, sum from body A and sum from all the other bodies. So what does that particular term look like? So here it is, integrating this over body A. Well, V, let's split it up into two pieces. The velocity of the center of mass of body A, and V bar, the velocity of the fluid element relative to that center of mass. So when you square it, you get V squared as 2V dot V bar at V bar squared. And grad U as the gradient of U from body A, and then gradient of U from all the other bodies, summed over all the other bodies. So this thing splits up into two terms, and the velocity splits up into, this V squared splits up into three terms. So we can look at all these terms in turn. This term, VA squared, times the gradient of U of body A, what is that? What's the value of that term? 0, remember. What's the value of that term? Why? I sucker you when the answer was 0, right? Then I asked why. Remember, VA can be pulled outside the integral, right? It's a constant. So we have rho star times the gradient of the potential of body A, and remember we had that anti-symmetry argument, say that's going to be 0. So that term can be thrown away right away. We have this term, V bar squared. Let me get my things in right order. Yep. We have this. Well, this is the inside body A, so we have to integrate over that. This is the gradient of body A's own potential. And you might say, well, what is that? The thing is, our assumption of reflection symmetry tells us that is 0. Right? Because this, whatever it is, it's going to only depend on body A, but it's a vector. And if body A is reflection symmetric, which is what vectors are going to be, this one or that one, it's going to be the same, so therefore it has to be 0. Okay, it's a simple symmetry, and perfect fluid bodies tend to be reflection symmetric, and it's hard for them to support odd shapes, and so it's not unreasonable to throw that term away. Now we have a term that's not so obvious. We can pull VA outside, but now we have a VJ, say, a VK, and a grad JUA, all within body A. You can't throw that away. It's a tensorial object. It's a 2-index object, so there's no argument to get rid of it. So we'll just write that thing as this tensor object HJK. So it's some integral that depends on the internal velocity distribution in the body and its own gravitational field. And it could be non-zero. We don't know. And then it's contracted with VAK because this one put outside. Let's look at this term. VA can be pulled outside, and so can the gradient of UB be pulled outside. We're not going to expand to get multiple moment effects. So this over body A is basically a constant because body B is so far away. So this can be pulled outside, that can be pulled outside, and this just gives the mass. So we have the mass of body A, V squared body A times the gradient of all the other potentials summed over all the bodies. So that's a nice post-Newtonian term that you can expect to find. Right? There's Newtonian acceleration, and there's a V over C squared correction. This term, this term goes to 0. Why? Because I pull VA outside. I can pull the gradient of U outside, again, it's a constant of the closed order. And so all I have is rho star V bar integrated over the body. Well, what is that? You have to answer. It's 0. So remember, this is the velocity of a fluid element relative to the center of mass. So it's V minus V of the center of mass. But the integral rho V is just mass times the center of mass, and so the two just cancel. Right? taken out the center of mass motion, so the average of this over the body vanishes. So that term goes away. And then we're left with a very interesting term. This is red, the external potential. You pull that outside the integral, and we have rho star v bar squared. And that's like the kinetic, internal kinetic energy of the body with a factor of 2. Okay? So this one simple term gives us a term that we expect, kind of a post-Newtonian correction to the Newtonian acceleration, but we have two terms that depend on the internal structure of our body. They depend on the internal kinetic energy, and they depend on some weird combination of the velocity and the internal gravitational field of the body. So you might start to worry, we harped on the equivalence principle at the beginning of this series of lectures about bodies falling with the same acceleration, and now we see a post-Newtonian order. We see at least the possibility that the motion of a body might depend on its internal structure. The thing is, we do the same kind of calculation for all the terms in that post-Newtonian equation of hydrodynamics, similar kinds of tricks, grab everything, pull it all together, and in general relativity at least, an extremely remarkable thing happens. You get a bunch of terms that depend on the internal kinetic energy. Some terms depend on the internal gravitational potential energy. Some depend on the integral of the pressure over the body. And some depend on the internal energy, the total of all the other forms of energy inside the body, thermal, magnetic, whatever. And these terms are all over the place. And you say, now what? The first thing you notice that these only occur in post-Newtonian terms, and none of this arises in Newtonian theory, of course, we know that. Within these post-Newtonian terms, it turns out that if you have a body that is quasi-stationary equilibrium, then many of these integrals are connected with each other. This is called the virial theorem. In ordinary dynamics in undergraduate physics, you learn about virial theorem. 2t plus v is a constant or is equal to 0 or something for certain kinds of motions. Well, for fluids, there are similar kinds of virial theorems that we can derive. And here's just one example. It turns out that twice the internal kinetic energy plus the gravitational energy plus 3 times the pressure must vanish for any fluid body that's in quasi-stationary equilibrium. It's a simple thing to prove in Newtonian theory, and we can use this, even though this is Newtonian expressions, we can exploit this in all of our post-Newtonian terms because they're already of post-Newtonian order. We might be making a mistake by using this Newtonian expression, but the mistake would be of higher order, i.e. second post-Newtonian order. So we're working in first post-Newtonian order so we can exploit any of these Newtonian relations in a post-Newtonian term.
Sir,
Yeah.
question. Why pressure enters at the virial theorem and also the internal energy?
For the virial theorem, it doesn't. And basically, the idea is to calculate the, look at the moment of inertia tensor, which is rho x I xj bar. This is all the internal. X is x minus the center of mass, and so on. And then calculate 2 time derivatives of this. Okay? 2 time derivatives, well, one hitting that, one hitting that will give, and let's not use a tensor version, let's just use the scalar version. So it's just x squared. So 2 time derivatives will give you a rho v squared, that's the kinetic energy. But then a time derivative will hit, one time derivative gives x dot v, the second one can give v squared, that's kinetic energy, but the other one gives x dot a, acceleration. Plug in Newton's equations of motion, the Eulerian equation of motion, manipulate, there's a grad p term in there, and that grad p term gives you the 3 times the integral of the p. But in this particular case, internal energy doesn't enter. It did when we calculated the conserved energy before, but not for this virial theorem. And there are similar ones that there's actually a tensorial version with indices that you can define, and there are others that you have to use. This is just one that I'm displaying. But when you use this, you can look at all the terms that involve T, omega, P, and so on. Some of them can be combined, and you can get rid of them using the fact that they add up to 0 in a special way. And when you're done, you discover a remarkable fact, that the only place where these internal quantities appear is in post-Newtonian corrections to the mass of each body. So we started off with this is just integral of rho star over each body. It's like the baryonic mass of each body. The only terms of this form that are left are terms that can be grouped together such that you can replace every mass in the expression with a new mass. And that new mass is simply this, plus that, plus that, plus that. And that's the kind of total mass you would expect for every body. Right? The real mass is not just the sum of the mass of the baryons. This includes the kinetic energy of motion in the body, the gravitational binding energy, and any other forms of energy in the body. So because of those virial theorems, you can renormalize all the masses in the expression and replace every mass by this new mass, which is the total mass of each body. So in the end of the day, every body, there's no remaining internal structure in the equations of motion for these n bodies. Each body moves as if it had mass given by this expression, and so all bodies fall the same way, independent of their internal structure. It's quite a miracle that all these things cancel at the end of the day to give this kind of result. And this, it turns out, is a manifestation of what we call the strong equivalence principle. It's a stronger version of the equivalence principle that I used earlier as the foundation for general relativity. It's one that says that bodies fall with the same acceleration even if they have internal gravitational binding energy. So stars and planets and neutron stars and so on, not just laboratory objects that have negligible gravity. But the unique thing about this principle is that it's certainly satisfied by general relativity, and there are many other manifestations of it that we can check. But it seems that most, if not all, alternative theories of gravity violate this principle somehow. So earlier mentioned the Brand-Sticky theory or scalar tensor theories. They all obey the Einstein equivalence principle. These are metric theories. They satisfy the Utbush experiment, gravitational redshift, all those experiments I talked about earlier. But that class of theories violates this principle. After you do all this, there are terms left over in the equations of motion that depend on the gravitational binding energy of the various bodies. And so the Earth and the Moon in those theories would fall with a different acceleration because the Earth is a little more gravitationally bound than the Moon is. So this is really we call it the strong equivalence principle because it really is a principle that includes gravitational interactions in the statement, and it appears that general relativity is unique in obeying. Yeah.
So how does the higher order post-Newtonian terms follow similar structures?
So at 2pn order, for example, you can do all this. Of course, you have to do things to higher order. You have to have post-Newtonian virial theorems, etc., etc. At 2pn order, you can show that it works. This is actually work that I did with a student about 7 or 8 years ago. So at 2pn order, general relativity obeys this principle. But beyond that, we don't know for sure. Simply because to go to higher post-Newtonian orders of these fluid balls that we describe our systems is just already at 2pn order it gets to be a mess. At 3pn order it gets horrendous. And so we don't know, and there's no rigorous proof that this really holds to all orders, although somehow we believe it must be true. But it's not been shown. Yeah.
And then, why do you think it must be true if it's not true?
I'm sorry?
Sorry, is there a reason why, is it just a coincidence that all these terms cancel out? Or is there a reason why it's not true?
Yeah, I mean, one way of thinking about it is that suppose you have a body that's bound, gravitationally bound. And you ask, how's this body going to fall, say, in the field of some distant body? Well, we can take this ball, this body, and surround it with sort of a quasi-inertial frame. Now, normally you think of a local inertial frame as having no gravity at all, right? But now we have this ball with gravity. But we can take a frame that's falling freely such that far enough away from this body, space-time is locally flat, but we just can't get too close to the body because we know it has gravity. Okay. So we have this body here, and we're freely falling with respect to some distant object. Now in the exterior region of this freely falling frame, we can make the metric be completely flat up to tidal corrections due to the homogeneities in the external field. And then you ask yourself, will this planet fall with the same acceleration as my freely falling frame? Well, what could make it do anything but fall with the same acceleration? How does this planet, inside my freely falling frame, even know that there's another planet out there? Because the metric at the boundary is just the Minkowski metric, and in general relativity, that's the only gravitational field there is. So there's no way for the field of that distant body to penetrate this freely falling frame to tell this gravitating body to do something different. The bottom line is it's really because general relativity has only one gravitational field, the metric itself. Now take a scalar tensor theory. You can do the same thing. You make the metric Minkowskian in this region far from our planet, but there's still a scalar field that can penetrate it, and it's a scalar. You can't change it. It's an invariant quantity, but it could have a value that depends on how close or how far that planet is, and that value, particularly in scalar tensor theory, governs the value of big G as constant. So if Newton's constant changes because that distant body is coming in and out, then the structure of this body can change. It could be more or less random, G goes up or down, and so suddenly this body knows that there's an external world. And then you can make nice arguments if its internal energy changes because G changes, then it has to accelerate in a different manner. So what distinguishes general relativity from all these alternative theories is that most theories, not all, introduce auxiliary gravitational fields, and they can penetrate the local frame and tell gravitating bodies that there's something going on out there and you have to respond to it. GR is unique. There's no such extra fields. So that's sort of the underlying reason why it seems to evade this principle.
And what about theories that are just parametric with higher?
Yeah, like R plus R squared theories, massive gravity theories. One of the problems with a lot of these theories that are being invented for cosmology and dark energy purposes is that they're so complicated that very few people have actually worked out their post-Newtonian limits in enough detail to actually see if this is true. I mean, it wouldn't surprise me if a theory composed purely out of the Riemann and Ricci tensors satisfied this because there's only one metric, there's only one field. On the other hand, we know, for example, that F of R theories where the action is just some chosen function of R, in some cases are really equivalent to a scalar tensor theory. So you have to be a bit careful about the interpretation of the theory. Maybe there are additional degrees of freedom in the theory that you didn't know about just by staring at the action and saying, oh, it only has the Riemann and Ricci tensor in it. There could be hidden degrees of freedom in some cases. So, but the bottom line here is that general relativity does obey it, and a lot of other theories don't.
If we looked at other forces in this post-Newtonian equation motion, would these be the inertial masses for the other forces?
Yeah, I thought about doing this calculation. Suppose you put a charge on one of these bodies, what would be its acceleration in the field, electromagnetic field of a distant object, and work on it in post-Newtonian theory, post-Newtonian electromagnetic theory combined. I don't know the answer. I thought about doing it back when I was young, but it certainly makes sense, just from a field theory point of view, that the inertial mass is the total energy of the body. And we'll also find out that this, for say a single isolated body, the globally conserved mass that we defined earlier in the post-Minkowski is just this, exactly that. So it ties together, but I couldn't tell you if a charged body falls with that inertial mass.
So in this case, we had a strong assumption that our body has reflective symmetry. So I would expect the strong equivalence principle is something taken for granted. I would expect it to hold true. But has anybody worked out the general case?
So this assumption was one that Eric Poisson and I made in our book. To keep the calculation to about 7 pages. Back when I worked this out in the parameter in the PPN formalism, I made no such assumption. There are a bunch of extra terms that are weird. So for like a pear-shaped body in certain theories of gravity, there's a self-acceleration. So the body, even if it's in empty space, will just accelerate off, toward the fat end of the pear, just by itself. So I made no such symmetry assumptions. Turns out that all of those effects depend on theories of gravity that are not based on the Lagrangian, that could violate conservation of momentum intrinsically. In any theory like general relativity, no such effects occur. So they could occur in principle in certain theories for our weirdly shaped bodies. They won't occur in theories like GR based on an action. So we could have included them and then thrown them away and had some big long multi-page discussion, and people say, "Oh, this is just." Tore out those pages and gone on to the next chapter. Or with that one very simple assumption, and it's a reasonable one for perfect fluids, everything cleans up nicely. So for pedagogical purposes, we made that one, but you don't have to. Other questions?
What about the other assumption that you said? I think you took the gradient of the potential from the other bodies to be uniform throughout this body. Where would that kick in? Would that
Right. So we already did that earlier on. We expanded those potentials and got all those multiple coupling effects. You could include them. You could also include post-Newtonian corrections to those things. And some people like Thibaut Amour and collaborators have looked a little bit at defining those multiple moments in post-Newtonian theory in a rigorous way, especially for solar system applications. So you could do it in principle. And it would just be added terms that you'd have to keep track of. Yeah?
Sorry, so what are the differences in the experimental test of strong and weak?
So tests of the weak equivalence principles that I discussed tend to be laboratory type experiments for the most part. How does the ball of aluminum and platinum fall in the field of the sun or the earth or some other object? So, because the internal gravity is irrelevant, you can use laboratory scale devices to test that fundamental principle. One of the most important tests of this principle is done in the solar system by lunar laser ranging, to measure whether the Earth and the Moon fall toward the sun with the same acceleration. And as I showed in an earlier graph, they do to about a part in 10 to the 13th. And that puts a very strong limit on any violation of this principle. And just recently, this pulsar in a triple system, the data from that has been analyzed. Neutron star and a white dwarf in the field of another third body, a white dwarf. The relative acceleration there, there's no difference in acceleration at the level of a part per million, which is a very strong bound, especially given that the neutron star has a huge amount of gravitational binding energy. 20% of its mass is gravitational binding energy. Whereas for the Earth and Moon, it's a few parts in 10 over 10. So it's a strong field test of this principle, and again, agrees with general relativity.
Can I another question? I'm a bit confused now because the binding energy usually defined as being the total mass of the system minus the bottom mass times the number of particles. But here it's apparently something different.
So what you can do is.
Is it possible?
My use of the term binding energy is probably a little too loose. I mean, this is just the total energy. And to work out the binding energy, first of all, you can use this virial theorem. You have a static surface symmetric body. This is generally negative because this dominates the other two. So for static surface symmetric systems, you can relate this to the binding energy defined in the normal way. Okay. It's just a different representation in this expansion. Okay, let's. So the final result, after you do all these calculations, after you replace the little n's by the big M's, so each mass gets renormalized by including its own internal energy, you get set of post-Newtonian equations of motion. Here are the Newtonian n-body equations that we've already seen. And then you see 1 over c squared times corrections that involve, very like the Newtonian acceleration, but with b squareds and the gravitational potentials and so on. But notice that capital M is the thing that appears everywhere here. So there's no dependence on the internal structure once you renormalize each baryonic mass with the total mass. Okay, well that's the n-body equations of motion, which might be useful, but let's specialize to two bodies where things are simpler and we have at least one example that we need to, one story we need to complete, namely for Mercury. So we take a two-body system, or simply the total mass of the system, the reduced mass parameter. We define the relative vector, R1 minus R2, and so on. A unit vector is a very useful thing to define, and then R dot is just the rate of change of the radius of the distance, it's the same as n dot v. And when you do that, those equations of motion simplify even more. So you have a relative, there's our two-body Keplerian, a Newtonian acceleration, and then you see the first post-Newtonian corrections. Notice that there's a piece that's radial in the same direction as the Newtonian acceleration, but there's also a piece in the direction of velocity. So the force is no longer a radial acceleration, there's a tangential part of the acceleration in addition. Sorry?
After you renormalize, the first post-Newtonian correction decides to be correction.
Yeah, those equations before were identical to the Einstein-Newton
Just after you renormalize.
The method they used was quite different than this, so at the end of the day, equations are identical. In fact, those equations were not derived by EIH initially. The first version of those equations was derived by a student of Lorentz named Johannes Droste in around 1916, just months after Einstein's published the full theory. But that calculation was actually sort of forgotten until fairly recently, because it was his PhD thesis, and he published it in the Dutch Academy of Sciences journal in Dutch, and it's not a language that scientists read too well, so people had forgotten about this Droste calculation supervised by Lorentz until some decades ago, when people realized he was really the first person to do it and get the right answers, long before EIH. Okay, so the first thing I want to do with this simple two-body equation of motion is to check what's conserved. We know in Newtonian theory the energy is conserved. What about in post-Newtonian theory? So to see if we can find a conserved quantity here, like an energy, let's take the acceleration and dot it into v. Okay, v dot a is just the time derivative of v squared with a factor of 2. So v dot a is just 1/2 d by dt of v squared. And on the right-hand side, we dot v into this. V dot n gives an r dot. V dot v gives a v squared. So we combine all those terms together and get our Newtonian piece, and then this post-Newtonian correction. Well, what we do is we know that this is a total time derivative. And so we pull that over there, so we get d by dt of something. And if we were doing Newtonian theory, the right-hand side would be 0. And so whatever that is, that's our conserved energy. And it was 1/2 v squared minus gm over r. So the idea here is to take this now at post-Newtonian order and see if we can pull out total time derivatives of something, push them all to the left-hand side, and that means d by dt of something will vanish, and that something will be our energy. But notice this is a bit more complicated than just this. This is obviously a time derivative. This isn't so obvious. But there are some simple things you can establish that this, of course, is a total time derivative. But you can also work out the fact that this is a time derivative. This, with r dot cubed here, is a time derivative. And so you can take all those terms and play around with them and kind of suck out time derivatives and see what you get. And at the end of the day, you discover that this is a time derivative, And this combination is also a time derivative of this expression, just using those identities that you established. Okay, so there is a conserved quantity. Push everything to the right-hand side, to the left-hand side, so d by dt of something vanishes. But I want to do a little trick that will illustrate an important point of establishing conserved quantities. This is what we had before. What I want to do is to subtract this from it. You say, well, how can we possibly do that? Well, if I think about it, I can do it for the following reason. If I just look at that Newtonian order, this is conserved. Right? This is the Newtonian energy. So d by dt of this is 0. But I put a squared in here, and 1 over c squared, so this is actually a post-Newtonian expression. So the fact that d by dt of the Newtonian energy is not quite 0, it has post-Newtonian directions to it. Since this is already a post-Newtonian order, that error would be a second post-Newtonian order. I'm ignoring those terms. I'm not going to 2p order, staying at 1. Okay, so I'm adding a post-Newtonian term that is constant to post-Newtonian order. Right? It's only non-constant at 2p order. Totally free to do that. And you say, well, how can you do that? How can you just add something to the energy like that? Well, one thing you know about energy is that it's not a terribly well-defined quantity. For example, there is no zero of energy. Unless you're really doing quantum field theory, and even then, if you talk about quantum field theory and technology, the zero of energy is really unimportant. It's changes in energy that are important. So the fact that I've added some apparent constant at 1p in order to my energy is completely irrelevant. Okay, you might accept that, but you say, well, why the heck would you want to do that? Well, now let's take everything here. It's all a total time derivative. Let's combine it all together and see what we get for our answer. And so I won't go through the algebra, but you discover this quantity whose time derivative vanishes to post-Newtonian order is the Newtonian energy that we're familiar with, and then this post-Newtonian correction. But the reason I did this, I added this special term, and of course I was very cunning in how I did it, I knew where I wanted to go with it, is that if you look at these two terms, the purely kinetic terms where there's no gravity, these correspond to the expansion in powers of V of what you would get for the total energy of two particles in special relativity. Right? The mass of two particles in special relativity is just the gamma factor for one particle times c squared, plus the gamma factor for the other particle times c squared. Gamma is 1 over square root 1 minus v squared over c squared. So if you take this thing and expand it in powers of v over c squared, convert to the relative velocity v1 minus v2, you will get exactly that. Okay, so I've added this constant to the energy and a relative constant to the energy just in order that in the absence of gravity, my answer would correspond to what you get in pure special relativity. That's an aesthetic choice. I didn't have to. I get a slightly different expression, but they all differ by something that is constant at 1p in order. But this idea of moving things into the energy, some constant stuff into the energy that you are free to do, will be an important fact. It's very useful fact, especially when we talk about radiation reaction, and it will feature in one of the exercises this afternoon. So I'm saying that so you can remember that fact at that time. So there is a conserved energy as a post-Newtonian piece to it. There's also conserved angular momentum. It's not the... You remember there was a velocity-dependent term in the equation of motion, a tangential term, so it means that h, the ordinary x cross v, is no longer conserved because there's a component of the acceleration in the direction of v. But it turns out that there's a post-Newtonian correction at 1 plus some factor times u over c squared. And maybe v squared over c squared. So there are post-Newtonian corrections, but they're still, at the end of the day, a conserved angular momentum. It's in the same direction as the Newtonian one, but it has some post-Newtonian correction pieces. You can derive that the same way we did here. Okay, any questions about these conservation laws? Okay, we've got this two-body post-Newtonian equation of motion. I want to finish the story of the Perihelion Shift because this is where it all comes out. We have our equation of motion. We have to take the radial, tangential, and cross-track component, or out of plane component. This is zero, of course, because you remember the acceleration is in the direction of n or v. There's no component out of the plane. So even in the first post-Newtonian order, the orbital plane always stays fixed. There's no change in inclination or line of nodes. Everything, all the action stays within the orbit itself. Integrate, plug these into the Lagrange planetary equations, integrate over one orbit, and you discover these four constants do not change. No big surprise in some sense, because those are related to energy and angular momentum. The orbit stays in the same plane by definition. The only thing that changes is the pericenter angle. And you notice that it's given by the sum of the two masses, and this is the semi-lattice spectrum, so your major axis times 1 minus e squared, 6 pi g over c squared. Now, in most textbooks, of course, you treat a test particle moving, say, in the Schwarzschild metric, and you work out the pericenter advance, and you get that answer, but it's just the mass of the inner body. We've not restricted our attention there. We've had two arbitrary masses, and it turns out the answer is just the sum of the two masses. It's probably not a surprise, but it's worth doing it just to be sure. It could have been, in principle, something else, some other function of the two masses, but in this case, at 1 p.m. order, it's just the sum of the two masses. And so for Mercury, put in the numbers for the mass of the Sun. The mass of Mercury is about 10 million times smaller, so we can ignore the mass of Mercury. Put in the orbital elements for Mercury, g and c squared, and you get the famous 42.98 arc seconds per century in complete agreement with all the modern analyses of solar system data. But of course, you can also apply this to other systems, such as binary pulsars. So for example, for the pulse-Taylor binary pulsar, putting in the parameters, you can convert A into orbital period, which is what's actually measured. Centricity is measured, and you find that for the measured masses, the advance is roughly 4 degrees per year. For the famous double pulsar, it's about 10 degrees per year, and there's one that has an even bigger pericenter advance. Clear which one it is. In fact, in the Post-Taylor binary pulsar, we didn't know the masses a priori, so measuring this, knowing the orbital period gives you this, centricity could be measured. So the data are actually used to measure the total masses, assuming that general relativity is correct. We gave an answer of 2.88, or 5 more digits of solar masses. And then other measurements, notably the gravitational redshift effect, would give the mass ratio. And so you could infer at the end of the day that the two individual masses, in each case, to about a part in 10,000. So here was a case where general relativity was actually used to make a measurement of neutron star masses, which is quite a nice application of the theory. And so I've shown this already many times, so that's the story is complete. We have total agreement with the current observations. Okay. Yeah.
When you're able to measure the Perihelion events to higher accuracy with the 2 p.m. correction in the
No, I mean, very unlikely. So there are a number of effects that are smaller than the leading general relativistic effect. We've already talked about the quadruple moment effect. That's at about 0.03 arc seconds per century. The sun rotates, so there's this dragging of inertial frame effects that in principle you could measure or be sensitive to. That's about another factor of 10 smaller than that. Then at a level of part per million, there are some effects that come from the kind of coupling between the general relativistic corrections due to the sun and the Newtonian corrections due to distant bodies. There's a coupling effect between these two effects. Basically, the sun curves space-time around it, and that affects the Newtonian interaction between, say, Jupiter and Mercury. And similarly, Jupiter curves space-time around it, and those relativistic corrections affect the interaction of Mercury with the sun. Those are higher order effects, and they occur at the level of about a part per million of the leading GR effect. This is stuff that I just did about 6 months ago in Phys Rev Letters. And the reason I looked at this was that there's a mission that's going to be launched in late 2018 called Bepi Colombo, which will put 2 orbiters around Mercury, and one of their goals is to measure the perihelion shift of Mercury at a part per million. So that's what motivates me to think about this. They might be sensitive to this kind of effect. It's sort of beyond simple post-Newtonian. It's post-Newtonian, but it's a post-Newtonian combined with Newtonian third-body perturbations to produce a set of effects at a part per million. The 2pn effects are 100 times smaller than that. So, not much hope. Yeah.
What about for the binary pulsars? Could 2pn come into play there?
People like Michael Kramer say that they might one day be able to look at 2pn corrections in a double pulsar. But I think there's a ways to go. They're not there yet. Sort of with more data, improved accuracy, it's possible, but nothing's happened yet. Okay. Okay, let's get back and get away from the near zone. So we've talked about the post-Newtonian equations of motion within that zone. Now let's return to the wave zone. This is a school on gravitational waves, so let's start to talk about waves. And so let me remind you that we have our wave equation. This is just abstract, simplifying all the indices, but at the end of the day, we know this is going to be the field, h alpha beta, and this source is going to be tau alpha beta, matter plus lambda Lifshitz plus harmonic terms. And we found our solution, we expand in the wave zone, and here is kind of our final answer. Sum over multiples, L derivatives of multiple moments of our source. This is the source energy momentum tensor. Multiple moments of 1 over r. We have to take the gradient, L gradients of this thing. Remember this gradient, each gradient acts both on r in here and on the r that appears in retarded time. Tau is t minus r. So you have to take into account both kinds of gradients, and we want to work this out in general. And so let's just look a little bit at the structure, the general structure of these fields in the far zone. And I want to look at them one by one, H00, H0J, and HJK. So H00, if I look here, let's just start with L equals 0, L equals 1, and then L equals 2 and beyond. So L equals 0, there's just this, there's no derivatives, there's 1 over r, there's tau 0, 0, and there's nothing there. So it's just an interval of tau 0, 0 over our near zone. Okay? I'm not going to worry about that far zone interval until a bit later. So this is just an interval of multiple expansion integrated over the near zone. Okay, so L equals 0 terms this. For L equals 1, we get 1x inside the interval, and we get 1 derivative and a minus sign. For L equals 2 and above, we just get the same expression, but starting with L equals 2, and so it starts with a quadruple term. So what does this term look like? This first term? Yeah, it's just the total mass, total energy of the system. So this is just m over r. And if you work this out to post-Newtonian order, including all the terms, you get exactly the same m that we described before. Baryonic mass plus various components of the energy. So this is m over r, kind of the leading piece of the Schwarzschild geometry that you would get for a simple static spherical symmetric body. Then there's this term, which looks like the center of mass, right? It's this energy density times x integrated over the manifold. So it's like a center of mass. And we know from the conservation laws that that center of mass moves uniformly. So we can always find a coordinate system that co-moves with that center of mass and choose the coordinate system so that that's at the origin of our coordinates. So we can set this thing equal to 0 simply by a choice of coordinates. This is just the mass times the center of mass location, and we can always find a coordinate system that makes that vanish, and it will always vanish as long as we have the coordinate system co-move with the overall system. And so the rest just consists of a set of multiple moments starting with the quadrupole moment. And so our general expression then for H00, the near zone part of it, integrated over the near zone, is M over R and then some derivatives of multiple moments starting with the quadrupole. What about H0J? Okay, so we have L equals 0, it's just the integral of this. L equals 1, one thing, and 1x, and then a bunch of moments starting with the quadrupole. The first term is just the momentum, right? Tau 0j integrated over the near zone. That's just the momentum of the system, and we can make that 0 because we've already chosen the center of mass to be fixed at the origin of our system, so our overall system has 0 momentum. Again, that's just a choice of coordinates. You can always do it. So get rid of that term completely. This term is a little more complicated, but it turns out to be quite nice because you can show, remember this thing satisfies an identity, the ordinary divergence of this thing. So partial alpha with T0 alpha, tau 0 alpha vanishes, so we can exploit that identity to find that relationship, to prove as an identity that this is equal to a partial time derivative of that plus that plus that. It's a simple identity you can work out in a straightforward way. So if we look at these expressions, this then becomes the time derivative of a quadrupole moment. This is a divergence, a spatial divergence. So I think we can convert this volume interval into a surface interval at the boundary of the near zone. And then all you have to do is ask yourself, are there any R-independent contributions there? Anything that depends on R you can throw away. You know it's going to be canceled at the end of the day by stuff from that other interval. Just ask if there's any R-dependent stuff. And generally speaking, it doesn't happen. Finally, we have this term. And this is an anti-symmetric combination. So the square brackets mean 1/2 of that object minus the thing with the indices reversed. This is an anti-symmetric combination of something that looks like an x and something that looks like the momentum density. Right? Tau 0j is like the momentum density. So an anti-symmetric combination looks like x cross p, and that looks like angular momentum. So this term splits up into a time derivative term, something that's going to look like angular momentum, and a term that we can throw away at the surface, as long as you inspect it carefully to be sure. So at the end of the day, then, one can show that H0j has a term, this anti-symmetric term actually produces a term that is n cross the angular momentum of our system divided by r squared. There's a term that involves a divergence of a time derivative of the quadrupole moment, and then a sum starting with L equals 2 of these these are momentum moments, current moments. This is tau 0j with a bunch of x's attached to it, not tau 0, Okay? And people sometimes distinguish between these things. The earlier ones involving tau 0 and higher moments are mass multiple moments. These are current multiple moments. And so that sequence of moments will then contribute to H. The leading term involves the angular momentum, and of course this is exactly the term that you would get at leading order in the Kerr geometry, for example, for a rotating black hole, or that you would get for the rotating Earth that's used to test frame dragging using gyroscopes and things. So that's a well-known effect for a body that's rotating that has some angular momentum. And then these are multiple moments. And finally, we have H, the spatial part. And just looking at the leading term, the L equals 0 term, so this would just be tau jk with no x's at all. Again, you could use this identity because tau satisfies this ordinary divergence identity. You can show that tau jk is given by 2 time derivatives of this thing, which looks like a quadrupole moment, plus a pure divergence. And then if you expect here, you can throw away that divergence term at the surface. So this thing can be rewritten. Pulling out this L equals 0 term, it becomes just 2 time derivatives of this quadrupole moment over R, and then stuff continuing at L equals 1, and these are some kind of tensorial moments of the system. All right? So this is sort of the general form of these fields. And now I want to get even more specific about these far zone fields, and I want to go into what Eric and I call the far away zone. It's like far away in a distant galaxy or something. In those earlier expressions, there were terms that fell off as 1 over r squared, right? For example, the angular momentum term fell off as 1 over r squared. These derivatives, when the derivative is this one, you get terms that fall off as 1 over r squared. Well, that's fine if you're not too far from the system. But if you're at a gravitational wave detector of 300 megaparsecs from the system, those 1 over r squared terms are absolutely negligible, right? All you care about are the contributions of the metric that fall off as 1 over r. So we're going to throw away anything that involves contributions that fall off faster than 1 over r. Because at the end of the day, we're interested in gravitational wave detection. So for example, in H00, this was our answer, but this, we can just get rid of this thing. And furthermore, we notice that there are some nice identities satisfied by the unit vector. It's the gradient of r. The gradient of 1 over r is this over r squared. The gradient of the unit vector itself is proportional to 1 over r. And the gradient of retarded time is minus the unit vector. So you can see that every time you hit something with a gradient, you can determine its fall off with r, and thereby just single out only the things that will lead to an answer that is proportional to 1 over r. So this was our general expression. So we can pull r, 1 over r outside, because the gradient of that is 1 over r squared. And when these gradients hit that, every time the gradient hits an n, you get another 1 over r. So in fact, we can replace all these L's with time derivatives. The spatial gradient in here, in tau, automatically produces something that falls off more as 1 over r. So if all you care about is the 1 over r part of the metric, then we can pull this outside and replace these with time derivatives, and each time derivative is the 1 over c. So you just get L time derivatives of the multiple moment. Similarly, in the H0J, this is the expression that we got. We can throw away this angular momentum term. It's really, in fact, seems fairly close to the rotating object. It has 0 effect in our faraway wave zone. And looking at these things using the same trick, we see we just get 2 time derivatives of this quadrupole moment times a unit vector. And then here, the same thing. We just pull out 1 over r and convert these spatial derivatives into time derivatives. And then finally, HJK, do the same trick. This depends on 2 time derivatives, a sequence of time derivatives of these higher order moments. Okay. So now we have an expression for the field, this H field in the far zone. What does it do? And there are many different ways to work this out or to describe it, but I'll just use one simple way and talk about the equation of geodesic deviation. So if you have two particles moving on a geodesic, so freely falling particles, which is sort of in our laboratory here on Earth, freely falling, they could be the mirrors of LIGO. They're not completely freely falling. Obviously, in the vertical direction, they're supported against gravity, but they're a very long period pendula, so in the horizontal direction, they can be seen to be moving approximately freely with no forces acting on them to some degree. They could be the two corner cubes in LISA that are just orbiting the sun, and two of the LISA spacecraft, so they're freely falling with no forces acting on them. So, as an idealization, we consider two geodesics moving through space-time. Each geodesic has a forward velocity, the tangent vector along its line, and then for geodesics that are near each other, you can also define a relative vector c that joins the two geodesics. And the question is, how does this c, this deviation vector, evolve with time? And we don't care about how it's the rate of change of c, because if two objects are going like that, sure, they're going away from each other at some velocity. That's not important. What we really care about is the acceleration of these two lines relative to each other. So it's the second derivative of c with respect to proper time along with the geodesic that is important. And I've probably done this in GR classes before. It turns out that depends on the Riemann tensor of space-time, contracted on the forward velocity of your fiducial geodesic twice, and then also contracted on this deviation vector once. And now let's put ourselves in the rest frame of this fiducial geodesic. So this would be in a co-moving inertial frame. So at this moment of time, this particle would be completely at rest. So in that case, U only has a time component, and C only has spatial components. And so we can simplify this thing, and proper time reduces to ordinary coordinate time of our inertial reference frame. So we can get a simple coordinate type expression for the acceleration, relative acceleration between these two particles in terms of this specific component of the Riemann tensor contracted into the deviation vector. Now, earlier I showed you a formula for the Riemann tensor in terms of the metric. You have to relate the metric g mu nu to our field h mu nu. Remember, they're connected by this Gothic metric to work out the determinant. So there's a few steps you have to go through to get from the physical metric g mu nu to our h mu nu. But you can do it straightforwardly, keeping the lowest order terms, plug it into the Riemann tensor, and you discover that the answer is 1/2 two time derivatives of a specific set of components of the spatial field HJK. These components are called the TT, or transverse traceless components. To get these components, you define this projection operator, which is the Kronecker delta minus nj and p, where n is the direction of propagation of it's sort of the gradient of this r. So it's the direction of propagation of the waves. We're assuming we have something that follows retarded time, so n is the gradient of r. So this selects out the component that's orthogonal, spatially orthogonal to the direction of propagation associated with this retarded field. And it's done in a specific way. You take each of these components and you project out in the orthogonal direction, and then you also get rid of the trace, because this is a trace. So you take this combination and you contract this on both indices with p, and the upshot is that the trace of this expression contracting on j and k vanishes. So this is transverse. N contracted with HJK is always 0. And it's traceless, because if you contract on JK, you get 0 automatically, no matter what the original H was.
What is capital N in this case?
I'm sorry?
Capital N?
So N is the gradient of R. So it's a unit vector in the direction of r. Okay, so I've said this, nj got contracted, this is 0, so it's transverse to the direction of propagation, and it's has 0 trace. And you can work out now in some detail, just choose a particular coordinate system, let n be in the z direction coming out of the blackboard, establish an x and y basis perpendicular to that, and show that for and then pick a particular set of h's and ask yourself what is the deviation between, say, two particles separated by some amount where the original orientation of the particles is spherical. You will see that in one direction the deviation of the particles is such that they come toward each other, whereas in the other direction they go away from each other. And in such a way that this tracelessness tells you that the area of the circle starts off as a circle is transformed to an ellipse. It tells you that the area does not change, so the total area within the ellipse is the same as the circle. And the motion is always orthogonal, so there's no deviation or motion of these particles in the direction of propagation of the signal. And you can also show that it turns out that there are only two independent polarizations of these waves. The other polarization is exactly the same deviation, but oriented by 45 degrees. Now, this is different from electromagnetic polarization, where the polarization of the E field can be in this direction or in that direction. Here, it's 45 degrees. It cannot be, the second polarization cannot be 90 degrees relative to the first. Why not? It would be the same thing. Right? Because 90 degrees, if I rotated this by 90 degrees, you couldn't tell the difference between the two. So it has to be something between 90, 0, and 0 and 90. In fact, there's a kind of a rule, and I don't know how strict it is, that the angle between the two polarizations of any field is given by pi divided by twice the spin of the particle that's responsible for the field. Okay. So think about it. So for E and M, the spin is 1, so the angle between the two polarizations is pi. For gravity, the spin is 2, so the angle is pi by 4, 45 degrees. For spinners, the spin is a half, so the angle is pi, so spin up or spin down, and so on. So it actually works. I don't know where this rule comes from, or if it's something you could derive from field theory, but it's a good rule for figuring out what's the angle between physical polarizations of a field. How's that related to the spin? Okay, now let's get specific about what this field might look like in the faraway zone for some particular source. So let's focus on Hij, because at the end of the day, that's all we really need, right? It's only the spatial part of the metric that is important for this geodesic deviation, for the response of our little prototype detector to a gravitational wave. So this is the only component we need, and we know that that is related to the lowest order in the faraway wave zone, which is dependent on two time derivatives of the quadrupole moment divided by the distance to the source. But I want to just emphasize that to get this answer, we had to iterate the Einstein's equations twice. You can't get the right answer by just doing linearized theory or doing one iteration. And this is something that a lot of, I think it's less common now, but 30 years ago, many people did not understand this point well enough. And certainly many particle physicists didn't understand it, because I've heard many claim all you need is linearized theory to get gravitational waves, and it's simply not true. And the reason it's not true is that if you calculate the first iteration, say of hij, that is given by an integral of tau ij with 0 plugged into it over x minus x prime retarded and so on. Okay? So on the right-hand side, I let h be 0, and I just calculate h from that. So that's just linearized theory, right? You put h equals 0 on the right-hand side, you calculate the linear first order in G expression for h. The trouble is, the equations of motion that are compatible with the gauge condition on h, namely grad alpha h1 alpha beta equals 0, the equations of motion that are compatible with that is that the divergence of this should vanish, grad alpha of tau alpha beta 0 equals 0. Well, tau with h set equal to 0 is just the special relativistic T alpha beta. Right? There's no Landau-Lifshitz pseudotensors. I said h equal to 0. Well, this says that the divergence of the special relativistic energy momentum tensor with no gravitational field appearing whatsoever vanishes. So that means that in that approximation, two stars going like this will move on straight lines and never interact with each other. The equations of motion compatible with linearized general relativity are no gravitational interactions between bodies. Well, that's clearly inconsistent with what we want to do if we want the gravitational waves from bodies orbiting each other. So this is why you have to go to the second iteration. You have to first iterate once and then plug h1 back into here to get h2. Because now the gauge condition on h2 is compatible with this thing with h1. And that's has the Landau-Lifshitz pseudotensor with h1, it has just a linearized metric in there, but it has the metric in there. And you could show that, for example, this, if you really boil that down, that will give you the Newton's equations of motion. Okay. So now you can have stars actually orbit each other because they would obey Newton's laws. Linearized theory is fine if you want to calculate the gravitational waves from a big dumbbell in your laboratory going around and around, and that's what Einstein did in 1916, because the dumbbell is held together by electromagnetic and electrostatic forces, not gravity. But if you want to calculate the gravitational waves from a system held together by gravity itself, you absolutely have to go to the second iteration, nonlinear. You have to include those nonlinearities, because only then do you have a solution that is consistent with at least Newton's laws at lowest order. The trouble is, of course, and what makes people make these wrong statements, if I do this and calculate h2, tau j h1, blah, 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 and I just look in the faraway wave zone, that little identity that I showed you allows you to convert this tau ij into two time derivatives of the quadrupole moment. So the final answer is 1 over r times 2 time derivatives of the quadrupole moment. But it's the same answer you would get for a dumbbell in your laboratory. And so that fools people into thinking that linearized theory is all you need. But it's just a fluke that you get an answer that turns out to look exactly the same. But there really is a difference, even in two time derivatives, because for a dumbbell, the two time derivatives involve the acceleration of the balls in your dumbbell, which will involve Maxwell's equations to produce the electrostatic fields that hold the dumbbell, that hold the rod together and not fall apart. But in gravity, the second time derivative, you've got to do something to make your bodies move around each other. So that second time derivative is going to involve g, which is so you can get Newton's acceleration. But since there's a g outside already, the g that comes from that second time derivative in Newton's law is g squared. And that's why you have to have two iterations. A solution that's compatible with the physics you're trying to solve. So even when people say, well, it's the same answer as the inverse theory, it really isn't. This second dot in a gravitational situation is a different dot than the one you would get in a laboratory situation. You want you to have a little dot prime or something to emphasize that the interpretation of that dot is different for the two physical cases. So again, I'm preaching it once more because this is the kind of debate that we, back in the 70s during the famous quadruple controversy, this was part of this discussion about whether one had the right number of iterations to get these kinds of formulas. Okay, remember our detector responds to only the transverse traceless part, so it's only the TT part that matters. And it turns out that if you're only looking at the TT part, you can put an STF bracket around here. It's symmetrically trace-free because the TT makes it trace-free anyway. And so, and this symmetric trace-free quadrupole moment is just given by that expression. And for an n-body system, you can calculate the two time derivatives using Newton's laws, and you get that expression. This quadrupole formula, this very simple formula, this is the lowest order approximation, is often called the Newtonian order result. Even though this, of course, Newtonian theory doesn't predict gravitational waves at all, there's sort of nothing Newtonian about it, but it's become now a convention to call this the Newtonian order result because we now have post-Newtonian corrections to these formula, all the way up to 3.5 post-Newtonian order. So it's just a nice convention to start somewhere, and so we just call this the Newtonian order result for gravitational waves. If you want to go to higher order post-Newtonian gravitational waves, you just have to keep iterating. So to get to first post-Newtonian corrections and the 1.5 post-Newtonian corrections, you need 3 iterations. You have to do this thing, plug it back in, and iterate once more. If you want to go to second post-Newtonian order, you have to do another iteration, and so on. The higher the order you need beyond the quadrupole formula, the more times you have to iterate these expressions to get all the terms you need to complete the calculation. Okay, so let me look at where we are, and it might be time for a break. Yeah, so why don't we take a break, and we'll pick it up again and finish off after 20 minutes or so.